All right, so you also might want to look at your Ames reference sheet for 9-5, tangents. If you look at the back, we are going to discuss this and this one up here. So we're going to discuss those two situations on the back of your sheet. Does anybody know what a line tangent to a circle is? Do you remember that from middle school, Seth?
It touches it in one place.
That's right. So a tangent line, and so that's what you have here for your definition, is tangent to a circle if and only if it intersects a circle in exactly one point. So it is a line that is in exactly one point, touches the circle in one point. And I can have an infinite number of lines tangent to a circle. And then the point at which it's touching the circle is called the point of tangency. And that's going to become an important point here shortly. So as you look at the circle down here below that I've drawn for you, I want you to add the following. So add the points. This point is D as in dog, B as in boy, and A as in apple. So draw a horizontal line touching these 2 points. So that's the tangent line to the circle, and B is your point of tangency. And then we're going to draw a radius from the center C to that point of tangency. And what you're going to find out in the next theorem is that if we draw a radius to the point of tangency, that angle created is always 90 degrees. They might not tell you that. You're supposed to know and remember it, and that's one of the big things that you're going to forget. And then draw a line from A to C. So off to the right it says a circle separates a plane into 3 parts. The parts are the interior, A and C are in the interior of the circle. The exterior, point D is on the exterior of the circle, and the circle itself. Point B is on the circle itself. Alright, so look at theorem 9-8. Bless you. If a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So if you have, bless you, a line that's tangent to the circle, it is perpendicular to the radius drawn to the point of tangency. Huge. And so that's what we're just talking about. So I want you to draw from this point here, and we'll call that point B as in boy, and then this is circle C. Try to attempt to draw a line that's tangent to that circle. That means that you just want that line to kiss the circle there at point B. Just tapping it there. You don't want it to go through the circle, you don't want it to miss the point. And then you can have a picture that's drawn just like this, and you have nothing in it, but you can create a radius yourself from the center to that point of tangency and create a right angle. There goes the voice again. So then let's look at example 1. You have a problem in your homework that's related to this. They don't draw you a picture. So I'm going to show you how to draw the picture based upon the story, and that will help you complete one of those problems in your homework. It says, if a spacecraft needs to eject its outer fuel tanks when it is 5,000 kilometers above the Earth's surface, how far will it be from the horizon at the time it ejects its fuel tanks? The radius of Earth is about 6,400 kilometers. So this is our spaceship. See this point right here? This is our spaceship. This is the center of Earth. And then from the spaceship's point of view, if it looks directly out, if you're out in space looking at the Earth, if you look directly straight across, you're going to see that horizon point. So I'm going to call that H for horizon, because that's what they're considering the horizon. If you've ever been to the ocean, Pacific Ocean, California, have you ever sat out there and tried to see how far the ocean would go? What does it look like? It just kind of, it looks like it just drops off, like there's a straight line out there, right? Well, that's a horizon. I mean, if you live in a state like Washington State, you probably don't ever see the horizon that often. Here in the desert, can we see the horizon in certain places? Yeah, I mean, we live in a valley here, so you have to kind of get out of the valley to see the horizon, but you can. So there's certain places you can see the horizon, certain places you can't. So let's go ahead and draw. I can actually draw a right triangle with this. S and H create a tangent line, and I'm just going to draw a line from point S to point H, a line segment. I could draw the whole line, but I just want to see the right triangle that occurs. The center of the Earth to the horizon point, that point of tangency, that's a radius of the Earth. It does create a right angle right here. You're supposed to know that. Then the question says, if a spacecraft needs to eject its outer fuel tanks when it is 5,000 kilometers above the Earth's surface. This is not 5,000 right here. Thank you. If you draw this hypotenuse to the triangle, the 5,000 is actually from S to this point on the Earth right there. That's where the 5,000 comes into play. So what's the distance from here to here? What information is there? Is this a radius of the Earth? Yeah. So this is 6,400. We would not, kilometers, we would not consider going down into the center of the Earth as part of that 5,000, would we? No. But we need to finish off our triangle, so we have to know what that additional distance is. And then from here to here is also 6,400 kilometers. And then the question is, how far will it be from the horizon? Isn't this our X? So let me blow that up a little bit. So that's what we're looking at. So when you have to draw your picture, draw one similar to that. Now if you put your spaceship way up here, I don't know, it just makes it a little bit more difficult to draw that triangle. That's why I tend to put the spaceship out to the side. So let's go ahead and solve that problem. How would you solve that problem? Yeah, Pythagorean's theorem. I essentially have two sides of a right triangle. So over here, we're going to take a squared plus b squared equals c squared. And then if you look at your picture, your a and your b are your legs. So we've got x squared plus 6,400 squared. So we've got x squared plus 6,400 squared equals, and then c is 5,000 plus 6,400 squared. So I'll help you with that. I won't give that to you on a test without a calculator, so I'd make the numbers much smaller. So we have x squared. 6,400 squared is 40,960,000 equals, and then if you add these together and square it, you get 129,960,000. So if I subtract the 960 and 960, those go away. So what's 129 minus 40? What's 129 minus 40? You figure it out. What'd you say? 89. So it's 89 million. And that's in kilometers squared, by the way. And I'll help you with taking the square root. So then from here, we take the square root of both sides. I'm not going to do a negative square root because that wouldn't be reasonable. So x is approximately 9,434 kilometers. So therefore, the spaceship is about 9,434 kilometers from the horizon. So when you do any of your word problems today, you want to create a picture that has a line of tangency to your circle, and most likely you're going to be creating a right triangle within that and using either Pythagoras theorem, or you might even use one of your special right triangles today. It's possible that you might use trig, sine, cosine, or tangent. So any of those are possibilities for any of your problems, so don't forget your prior knowledge. So then let's flip. So theorem 9.9 is just the converse of the previous one. In a plane, if a line is perpendicular to a radius of a circle at the endpoint on the circle, then the line is a tangent of the circle. So all this picture is just saying this line AB, since we see a right angle there, we can assume that AB is tangent to that circle without them having to tell us. So then look at this picture that I've given you here. Example 2. Determine whether RT, right here, determine whether RT is tangent to the circle S and explain. What are you going to add to the picture, first of all? Tell me what you see or what you know. SRT is 90 degrees, right? If we're going to assume that this is a point of tangency, because we're trying to prove that RT is tangent, so we're going to make the assumption that R is a point of tangency. So I'm going to make the assumption that the right angle is there at angle R. So in order to determine if this is a right triangle, I need to use what? Pythagoras theorem. We've done that proof in the last chapter, right? So we've got, again, a squared plus b squared equals c squared. Let's see if we have everything that we need to do that. It doesn't matter which is a and which is b. So this is our a and this is our b, because your legs are always your a and your b. Is c 8? Does that make sense? If this leg's 12 and that leg's 16, that c would be 8? No. So this is missing, and oftentimes it is. What should be there? What part of the circle is this? It's a radius. Yeah, isn't that a radius? So don't forget about the fact that radii are all the same. And so you have to make that conclusion that from S to P is 12. So now our C is actually 20. So in my formula, I'm going to plug in 12 for A, 16 for B, but 20 for C. So go ahead and do the math. We get 144 plus, what's 16 squared? 256. What's 20 squared? 400. And then you're not doing any solving, you're showing that the left side equals the right side. So if you add these together, what do you get? You get 400. So 400 does equal 400, it checks. So therefore, if angle SRT is a right angle, I'm going to squeeze that in there, and since triangle SRT is a right triangle by Pythag theorem, then RT, segment RT, is tangent to the circle. And then below that, we've talked about common tangents. So I showed you two different pictures of common external tangents versus common internal tangents. And it's just what happens between the circles? Do the tangents touch the circles outside, or do they intersect in between the circles? So you can highlight anything there that you would wish, but I just wanted you to realize what common tangents inside, so these are outside and these are inside, look like. And this is just the distance between the centers of those circles. So if the external tangents, or if the internal tangents cross at that distance between the centers, they're considered internal. If they don't cross, they're considered external. So flip it. You're going to get a lot of pictures that look like a dunce hat, right? It does not look like a dunce cat. So these are great and easy problems to solve. Theorem 910 says that two segments from the same exterior point, so here's your same exterior point, and then these are the two segments that we're talking about. They are tangent to the circle, then they are congruent. I don't know what they are, but they are tangent to the circle. How do I know they're tangent to the circle? Here's a radius that is touching a point of tangency, and they're telling me that's a right angle. Immediately I know that point Q is a point of tangency and point R is a point of tangency. So if this is 10 units, then this is 10 units. If this is 5,000 units, then this is 5,000 units. So that'll be important. Couldn't I connect C to P and create two right triangles? And they would end up being similar right triangles, because this leg and this leg would be congruent to this leg and this leg, and then they share a side. So by SSS or LL, I could prove that the triangles are congruent, and then we could use that information elsewise. So a lot of that part knowledge is coming in. You could also end up again with 30-60-90s or 45-45-90 triangles. Then circumscribed polygons. So we looked at inscribed quadrilaterals, which were inside the circle, but we use lines of tangency to create these circumscribed polygons. And you'll note that here's a point of tangency, here's a point of tangency, here's a point of tangency, here and here. The nifty thing about this that we're going to use down here is that according to the theorem above, isn't this an external point? So what that's saying is that this segment, I guess I'll use paint, this segment here is congruent to this segment here, from here to the point of tangency only. From here to the point of tangency only. I can do that all the way around this figure. Here's my 2 points of tangency, here's the external point. That means that these are congruent to each other. And then these will get triple tick marks, quadruple tick marks, and we're running out of tick marks, right? So you get the idea. I could do the same thing here. If these are my points of tangency here, then these pieces are equal, these pieces are equal, these pieces are equal. So how does that help us? Look at the last problem down here. So triangle TRW is circumscribed about circle A. If the perimeter of triangle TRW is 42, so that's something that'll be important in a minute, so I don't want to forget about that. Then they're telling you the measure from M to R is 6. So I put that down here for you. And then the measure from WM is 7. Find TR. So using that previous theorem, can you tell me what other lengths that you know? LR is what? 6. What else? KW is 7. Do we know TL? Well, it's not necessarily 6, it's not necessarily 7, but I do know that TL is congruent to TK, correct? And if I don't know what something is, what do I assign it? An X. So I'm going to let this be X and this be X. Equation to solve. My perimeter is 42. Walk around this figure, right? Isn't that the perimeter? Walk around the figure. So if my perimeter is 42, then wouldn't I take TL plus LR plus RM plus MW plus, running out of room, WK plus KT. Haven't I walked all the way around at this point? So I'm going to plug in things that I know. I know that my perimeter is 42. And I know that TL is X, and then LR is 6, and RM is also 6. MW is 7. Obviously they're short away, but this is your note, so I want you to be clear. And that, last but not least, we have X. So what does a 6, 6, 7, and 7 add up to? Yeah, so we've got 12 and 14, right? So there's your 26. And then how many X's? So we've got 2X plus our 26, right? So you go ahead and solve that. So what's the question? Does X answer that question? No. So TR is equal to X plus 6. So we're going to replace X with 8 plus 6. So the distance from really 14. So you have two parts to your homework. One part is practice, and the other part's from your textbook. So I'm going to get you started on your practice. And I'll do several of these with you. Alright, so let's see how these apply. Every day is a little better than the next. Alright. Alright, so let's look at number 1. So the directions say find the value of X, assume that segments that appear to be tangent are tangent. Alright, so what do you conclude about this picture here? What's your equation to solve, knowing the theorems that we just talked about? What do you know about this segment here and this segment here meeting at a point external to the circle? They're congruent. So you're going to set 3x plus 4 equal to 40. If you know how to set up the equation, the solution's easy. The hard part is setting up that equation. So go ahead and solve. What's x? 12. All right, look at number 2. What observations can you make about 2? All right, so we have a right angle right here. How are you going to solve for x? Are we missing any values? All right, so what's the distance from P to C? X. Well, you didn't have an x in the problem that I gave you in your notes, so let's see how that affects the problem. So we will use Pythagoras theorem. So we've got x squared plus 12 squared, those are your legs, equals, is this 8x or is it x plus 8? Alright, so watch how this works. X plus 8 squared. X plus 8 squared is not x squared plus 64. It has a middle term. So if you don't know your factor pattern for that, then you need to actually write this out and FOIL it. So we get x squared plus 144 equals, you multiply this out, you get x squared plus 16x plus 64. You would have missed your middle term of 16x. Fortunately, if I try to collect my x squares, what happens? If I subtract an x squared from both sides, don't they cancel out? So you should be going, phew, why? That means we don't have to factor, right? So then we end up with 144 equals 16x plus 64, and then solve from there. Bless you. Did you get 5? All right, so that wasn't so bad. Now look at number 3. So 3 is a little different. What can you tell me about 3? It's actually easier than it looks. How are we going to find x? Very good. BC is 3. Why? Because it's congruent. These two pieces are congruent because they both meet at a point outside the circle and they come from points of tangencies. So what else do you know? Yep, these two are congruent, and so CD is 4, so what's x? 7. So that was baby math, right? The only point was that you need to be able to start to recognize what parts are congruent. All right, let's look at 4. They have a 60 degrees in here. That should be putting bells in your head, right? So let's see what we have. We've got a full right triangle here. If this is 60, what do I know about this here? It's 30. What do I know about AC and BC? They're congruent. And technically, I could draw a radius from P to B, couldn't I? And wouldn't I have a right angle here? Are you with me? So, and isn't this 90 degrees here? So if this is 90, what's this little angle here? 30 degrees, okay. And then if that's x, this is x, isn't it? And if that's 6, isn't this 6? So here's what I'm going to do. I'm going to pull this little triangle right here, this little one right there, I'm going to pull it out over here to the side. I'm going to redraw it out here so it's bigger so I can work with it. So all I did was take this triangle here and redraw it over there. So this is point P, this is point D, and this is point B. So based upon this, I know that this is x. I know that this is 30 degrees. And we know that this is 6, right? That that's 6, this is 6. Because, how do I know that? Isn't this part of a diameter coming to a chord, and isn't it perpendicular? And doesn't it bisect the chord? There we go. Do I know how to solve that kind of a problem? If it's a 30, 60, 90, here's my 60, I'm concerned about x. I really don't care about what's crossing the 30, but we're going to use our pattern 30, 60, 90. What's our pattern for that? 1 red, 3, 2. So make your fractions. I don't know what's across from the 30, but that doesn't bother me. So I'm going to leave a blank down here. I know across from the 60 is 6. So below the red 3, I'm going to put a 6. And across from my hypotenuse is x. So this is the proportion I want to solve. So we're going to cross multiply. So I get x radical 3 is equal to 12. Divide by radical 3. I get x is equal to 12 radical 3. Is that an acceptable answer? What do I have to do? Yep, we get to rationalize. So this is rad 3, rad 3. So I end up with x equaling 12 radical 3 over, this gives me just a 3. Now am I done? Nope. What's outside the radical can reduce with what's outside the radical, so I can reduce the 12 and the 3. And I get a final answer of 4 radical 3. So that one was a little bit more involved, right? A lot of things you have to see and conclude. What about number 5? Tell me what's missing. There's 2 things are missing. PA, what's PA? 4, because it's the same as this radius, right? What else is missing? What do we know? Yeah, that angle right there is a right angle. So go ahead and solve. You solve on your own. Set up the equation. Is that a nice perfect square? True or false? 128 is perfect square? No. So don't have to take the square root of both sides? How am I going to find the square root of 128? Prime factor it, right? 4 goes into 28, so 4 goes into 128. And then 32, if you're not already aware, is 5 2s. And 4 is 2 2s. That's a lot of 2s. How many pairs should I make? 3 pairs, and I have a 2 left over. So x really is 2 times 2 times 2, so there's your 8, and the 2 stays underneath the radical. 8 red 2. Now, last problem. Looks a little intimidating, doesn't it? What do you notice? Aside from looking at the clock, what do you notice? So they've given you 12, right? The diameter. Do I have a right triangle in here at all? I have this one here, right? If I knew this measure, I might be able to find what I'm looking for. Tell me if I can do this. And if I can do it, how does it help me? How does this help me? Isn't this a right angle right here? Do I know this length here? This is 6 because it's half of 12. And this is also 6 here, so isn't this whole length here 10? Can I use that information to find this length here? So I'm going to leave you off with this. I'm going to make you finish this for homework, but you're going to use Pythagoras' theorem. You're going to find this length here, which doesn't answer your question. But once you have this length, can't you use Pythagoras' theorem a second time to find x? All right, so you'll finish that for homework in addition to your book page.